Welcome everyone to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's presentation is part of our series on the NGSS Cross-Cutting Concepts, Energy and Matter, Flows, Cycles, and Conservation. Our presenters are Charles W. Anderson, commonly known as Andy Anderson, and Joyce Parker. We also have Ted Willard online with us. He's Director of NGSS at NSTA to provide information on the standards. My name is Bryn Slate. I'll be moderating the program. And we have Jeff Lehman online with us to provide technical support. Before we jump in, I wanted to remind everyone to visit the NSTA Learning Center, which is your online portal for over 10,600 resources for science educators. And we've got over 3,700 resources in the Learning Center for free. And when you choose a resource, you can add it to your My Library area so you can get to it when it is a good time for you. We have community forums that are a great place for you to connect with other science teachers. If you need help finding information and resources there in the Learning Center, you can reach out to our online advisors. And we also have free tools that are available to help you organize your professional learning and meet your goals. And it is all available by going to learningcenter.nsta.org. And now I'd like to introduce our presenters today. As I mentioned, Ted Willard is here with us from the National Science Teachers Association, and he's our resident expert on the NGSS. Our featured presenters tonight are from Michigan State University. We have Charles W. Anderson, otherwise known as Andy Anderson, and we also have Joyce Parker with us today. And before we jump into our featured presentation, we're going to hear from Ted Willard, so I'll turn it over to Ted now.
Thanks, Bryn, and thanks everyone for being here tonight. I know as the school year drags us on, we get into the spring, it gets harder and harder to find some time to do things like this, so I appreciate your initiative and learning about some pieces. We got a great piece tonight. I want to just give a little start here just to get us all in the sort of same frame of reference here on the NGSS. As we mentioned many a time, there are 4 organizations that were involved in the development of NGSS. You've got the National Academies, Achieve, NSTA, and the American Association for the Advancement of Science. And a 2-step process in developing these standards. Back in July of 2012, the Framework for K-12 Science Education was released by the National Academies of Science. And to give a little sense of that book, if you haven't had a chance to look at it, I strongly recommend that you do so. You can get a free PDF from the National Academies of Press at their website, or you can also buy a hard copy of the book at NSTA Press. And as I've heard some people say, read it, and once you've read it once, go back and read it again. It's often a good idea. The practices described in the framework, there are 8 scientific and engineering practices, and NSTA did a web seminar series around those practices last fall. If you want to hear more about those, I suggest you go back and look at the archives of those. And then we have cross-cutting concepts, which we are focusing on this evening. And specifically tonight, we're doing energy and matter. But you can see the entire breadth of the different types of cross-cutting concepts there. The framework also outlines some disciplinary core ideas: life science, physical science, earth and space science, and then also engineering being added into the set of ideas. Each of these broke down into more specific ideas, and each of those into even more specific ideas. And finally, the standards themselves have very specific bullet points about ideas students should know. The second phase in this whole process was the development of the standards themselves, and as I've mentioned, Achieve coordinated that effort, but it was really run by 26 states that are listed there or highlighted there in blue. Each of these states had an opportunity to do formal reviews at several different points, the public and private reviews in this, and each of them made serious consideration about adopting the standards. Is going to be going through the process of considering that. They promised to do so. The states in white there, even though they weren't formally involved in the process, and that many of them did go through and do reviews at different points, and many of them are considering to adopt the standard. They're all welcome to. Just to give you a sense and a look of what these standards look like here, here's a sample from the standards. It's actually pulling still from the January draft. But it goes through, we have this idea here, a performance expectation of develop molecular models of reactants and products to support the explanation that atoms and therefore mass are conserved in chemical reactions. So this idea combines a practice here of develop molecular models to support an explanation. It had ideas in terms of just more core ideas that reactants and products combine and interaction, that atoms and therefore mass are conserved in a chemical reaction. And the idea of a cross-cutting concept that matter and energy is conserved is represented in this statement as well. Now, an important key in all of this is noted down here. The performance expectations combine these different elements together, but they're a statement not of what is to be taught in the classroom, but what is to be assessed at the end of instruction. Educators, classroom teachers, districts all have a lot of choices they can make in helping students gain the ability to engage in the practices, an understanding of the content, and of the cross-cutting concepts. And so educators can make any choice they want to about how to go about pulling these together. And it's once that instruction is done, we get to large-scale assessment, statewide assessments. The assessment, it would be expected to go and have them develop these molecular models. And so with that basic introduction to the whole process here, I'm going to turn things over to Andy and Joyce. Thank you again for being here, and we'll go ahead.
Hello, everyone. This is Joyce Parker.
And this is Andy Anderson.
We're here tonight to talk with you, as Ted said, about energy and matter, flows, cycles, and conservation. But before we do that, it would be helpful for us to know what age students you work with. So if you could do, as Bryn showed you, and click in whichever of these grade bands applies to you, that would be very helpful to us. And while you're doing that, I'd like to say we've tried hard to choose a variety of examples that cross disciplines and age groups, but if at any point you would like a different example or have a question about an example, feel free to write in your questions. We will be stopping several times to take questions. So it looks like so far middle school and high school are neck and neck.
And Joyce, I'll give just another moment here, and then I'll publish our graph of responses to the whiteboard.
Okay.
While we're waiting for the few final responses to come in, we've got a few folks saying in the chat that the volume level's a little bit low on your end. So if there's a way to increase that mic volume just a little bit or come in a little bit closer, that'd be great.
Okay, we upped the mic. Is that helpful?
That's much better, yes, thank you. And I'll go ahead and put up that graph so we can see where everybody's at there, and I'll turn it back over to you to discuss.
Okay, that's great. It makes a lot of sense. The matter and energy as cross-cutting concepts are most applicable to the middle and high school grades, so it's good to see you folks out there, but we hope we have something for everybody in the audience. So as Ted said, we are here to talk about energy and matter as a cross-cutting concept. Here you can see it in the list of 7 cross-cutting concepts in the next generation science standards. And as you look at it, you notice that it's slightly different from the others because it represents concepts that are also listed in the disciplinary core ideas. So what's so great about energy and matter? Why are they elevated to this status of cross-cutting concepts? Well, there are really 2 answers to that question. One is that they are cross-cutting. Conservation of matter and energy apply to everything, to all systems. no matter what their scale is, from subatomic up to universal, no matter what kind of system they are, physical, living, man-made, and they complement many of the practices that we're supposed to be teaching, such as explaining, predicting, modeling, designing, investigating. But also, they are special because they're conserved quantities. And what that means is that we can trace them. For example, if we know what matter is present at the beginning of a process, we should be able to find that matter back at the end of a process. And if our account of that process has matter in the form of atoms or molecules appearing or disappearing, we know that we've made a mistake, or there's something that we don't understand about the process. So in that way, these are very, very powerful ideas. So in today's webinar, what we want to do with you is explore this idea of what it means to use energy and matter as a cross-cutting concept. And after that, we'll talk about learning progressions and what they tell us about how students develop ideas about matter and energy. And then we'll spend just a short amount of time at the end talking about how to teach the use of matter and energy in this way. So let's take this first idea, what it means to use energy and matter not as just pieces of content, but as cross-cutting concepts. And we're going to address this in three ways. We're going to look at conservation laws as rules that we can't break and that tell us when our science stories are going awry. And we're going to apply those rules to different systems at different scales. And we'll give you some examples of how we think about that. And we will spend a little bit of time thinking about why all of this is hard. It's hard for students to think in this way. So before we think about conservation laws as rules in science, let's think about, take an example of rules from English grammar. Look at this sentence. He are 16 years old. As soon as you see that sentence or hear that sentence, if you're a native English speaker, you know something's wrong. A grammar rule has been broken. And it's in that sense that we think of the conservation laws as rules. They tell us when we've made a mistake. They tell us when we don't understand something or we're missing something. So here's an example from biology of the same idea. Breathing converts oxygen to CO2. Well, if we're thinking like a scientist, we know immediately that we've broken a rule because we have a carbon atom appearing out of nowhere. And our rule about conservation of matter says that that can't happen. We have to be able to explain where that carbon came from. So we see matter and energy conservation as these rules, and we want to apply these rules to science systems. And I call this the table of everything because it has all of the universe in a set of hierarchical systems, from very teeny systems the size of nuclei of atoms up to our macroscopic scale, the human scale that we're familiar with in our everyday lives, all the way up to the astronomical scale of galaxies and solar systems and things like that. And as we move scales, the matter that we have to think about changes also. So down at the nuclear scale, we worry about protons and neutrons. That's the matter that we pay attention to. And then as we get up to the atomic and molecular scale, we think about matter as atoms bonded together in different combinations to form different molecules. In our everyday world, the matter that we talk about are the objects around us, the solids, the liquids, the gases, made up of all different kinds of substances. Once we get up into the bigger scale systems, we talk about spheres, and we name those spheres according to the matter that we pay most attention to. So, for example, in the geosphere, there are living things in the geosphere, but what we pay attention to are the bits of rock, the rock assemblages, and the rocks that make up the tectonic plates. And finally, at the astronomical unit or scale, the matter that we pay attention to is mostly gases. Some rocky stuff in planets, but mostly gases in stars and groups of stars. The energy that we pay attention to in these systems changes also. So down here at the nuclear scale, the energy comes from interactions of particles with the strong forces. At the subatomic and atomic molecular levels, it has to do with electrical forces. And then from the human scale on up are the more familiar kinds of energy, the energy of motion, chemical potential energy, gravitational energy, light, and heat. So this is what we're going to talk about today. Energy and matter conservation is rules applied to systems. And we're going to work through some examples. It's the best way to illustrate this. And we're going to take our examples from this middle green section, sort of the middle scales, because those are the scales that we're all most familiar with. So here is a simple food web. And we can ask students to draw arrows and label them showing the matter going into and out of each of these organisms. And even pretty young children can draw some of these arrows. But even the oldest students tend to forget some of the arrows. But if we ask them to check to see if they've conserved matter, and we talk with them about what that means, they can correct and complete their pictures. So for example, the robin, kids often draw the water going into the robin. They know robins drink. But they don't think about what happens to that water, that water is there the next day when the robin drinks some more, and the next day when it drinks some more. And this poor robin is getting awfully full of water. And if you talk with them about it like that, they begin to realize that that has to be a two-way arrow. Somehow the water's getting back out of the robin, and they can usually figure out how that works. Here's an example of tracing energy at the macroscopic level. Here's a Rube Goldberg machine. These are amusing because they have many, many complex steps to accomplish something that's really very simple. In this case, the napkin wipes the mustache after the guy eats some soup. But if you want to build a Rube Goldberg machine, you have to think about energy. Every step of the Rube Goldberg machine transforms energy or transfers it to another object. And often, some of the energy leaves the system. For example, over here is a rocket. When that rocket goes off, it's going to cut this string, but it's going to take a lot of kinetic energy with it out of the system. So to have enough energy to make all these steps work, if you really want to build a Rube Goldberg machine, you have to build in some potential energy. The rocket has chemical potential energy in it. Here, the string pulling on the pendulum has potential energy, and energy is the key to making these machines work. Let's go down one scale now to the atomic molecular level. Now we're not going to think about objects anymore like crystals and lava. We're going to think about the atoms and molecules in them and how they move and are arranged. So in the crystal, the atoms of silicon oxide are arranged in a nice array and they just move around in place. But in the lava, they're moving randomly past each other. And that helps us understand why it takes energy to melt the crystals. We have to get these molecules moving fast enough that they can break out of their array. And we can take this idea of phase change up to the big scale of the water cycle and use it to explain each of these arrows that has to do with a phase change. There's evaporation, condensation, freezing, and thawing. And we know from what we learned at the smaller scale that each of those involves keeping the matter the same, but changing the way the molecules move and are arranged. The atomic molecular level also tells us about chemical changes. In chemical changes, atoms are conserved. So let's look at a simple one. We have hydrogen gas, oxygen gas, combine them and we get water. We have all the atoms here in the water that we started out with in the gas. But we had to put energy in to break the bonds in the gases, and energy came back out as we made water. So this model helps us understand how energy and matter are related to each other in chemical reactions. And the fact that they are related to each other makes it confusing for kids because it seems like they should be able to just trace matter and the energy will go along, but it turns out that doesn't work. So we can apply those ideas back to our little food web. We've already looked at the matter going in and out of each of these organisms, but we ignored the chemical reactions that were going on inside them. And the most important of those reactions are photosynthesis and cellular respiration. And in photosynthesis, what the plant is doing is taking the energy of sunlight and converting it to chemical potential energy in sugar. And based on what we just learned about bonds, that means there's less chemical potential energy in the bonds of carbon dioxide and water than there is in sugar. And that's why sugar and compounds like it are so valuable to living things. All these living things do the opposite reaction, cellular respiration. They transform the chemical potential energy in the sugar to chemical potential energy in something else, and they use that to get the work done in their cells. So we've gone from atomic molecular to to our macroscopic level. We can take this idea one step higher to the ecosystem scale. And instead of thinking about individual organisms, think about a whole ecosystem. And what we see is that energy in the form of sunlight is in the process of photosynthesis is converted into chemical energy in molecules and living things like sugars. And there are those sugars, a lot of things can happen to them. They can be made into other molecules. They might, the organism might be eaten by another organism or die, but eventually cellular respiration or combustion happens, and that chemical potential energy ends up as heat or work. And at that point, it's no longer any good to the system. It can't be recycled. Plants can't take heat or moving things and make sugars back out of them. So that's why energy, shown here with the red arrows, flows through an ecosystem and is not recycled the way the matter is. Okay, so I've been doing way too much talking here. It's your turn now. We have here 5 statements about a burning match, the matter and the energy in the burning match. So let's try to use what we've just been talking about to see if these, identify which of these statements are true and which ones are false. So I'm going to turn this over to you, and then we'll come back and talk about this.
Thanks, Joyce, and I'll just jump in and remind folks about the clip art, where that is located. You'll see it on your screen marking toolbar, which is the long, narrow strip right alongside of your participant window. And you can click on the bottom button there and select a shape to place in the appropriate column for each statement. It looks like we've got a lot of people working already, and they're moving down the line there, so we'll give folks just a few more moments to put their stamps up.
Yeah.
And Joyce, whenever you're ready, we can pause the clip art and discuss, and then we can turn to the next slide whenever you're ready for the answers.
Okay, I think we're going to look at the answers. I think the spread here shows us how hard it is to interpret these seemingly simple statements, which is something we should remember when we think about how to teach this material. So I'm going to go ahead and show the answers as we think about them, and talk about these one at a time, because they do illustrate what's hard about this and the complexity, not the complexities, but just what's hard about this kind of thinking. So we had a sort of even distribution for the first one. A lot of people saying it's true and a lot of people saying it's false. And you can see why there is some difference there. the statement says that heat and light energy are produced when the match burns, and that is absolutely correct. So that's an energy statement, and so to account for that energy, we have to identify the kind of energy that it came from. And it came from chemical potential energy in the wood. So you could say this is semantics. What we're saying is kids often misinterpret this to think about the matter in the wood ending up as energy, light, and heat. And so crisscrossing our energy stories with our matter stories is what makes this all pretty hard for students. Do you want to add anything to that, Andy?
No, I think we'll get to that. This is a very prevalent problem, and we're often careless when we start talking about glucose as a form of energy or ATP as a form of energy. But we feel that it's really, really important to make sure that kids separate forms of matter from forms of energy. So if wood is a form of matter, then that wood is not going to become energy.
Yeah, so, and these next three sort of clarify that. We're used to saying matter is conserved. It can't be destroyed. But matter is a kind of vague word. What do we mean by matter? Do we mean the wood? Do we mean the molecules in the wood, or do we mean the atoms of the wood? Well, if it involves a chemical reaction, really the only thing that is not destroyed are the atoms. The molecules in the wood are destroyed despite our little mantra that matter is conserved and never destroyed. So it's really only at the atomic level that that holds true. And so, of course, you can see this is very confusing for students. The last statement talks about mass. And we find it easiest to help students understand this by associating mass with atoms. And since the atoms were not destroyed, the mass was not destroyed. So we've used this question to illustrate two important ways that using matter and energy as a cross-cutting concept is difficult. It's easy to mix up the matter and the energy stories, but we have to trace them separately, and our language often gets in the way of what we're trying to convey to students. And with that, I'm going to push on.
Actually, let's go ahead and show the.
You want to go back one? So this.
And actually, I'm going to show both of these. I think these are both important.
Okay.
For sake of time. Yeah.
So what we're saying here is these are statements here are examples of how our everyday language kind of gets us into trouble separating matter and energy. The burning match loses mass because some of its mass is converted into energy. Well, again, it's not the mass. We have to be careful. It's not the mass being converted into energy. It's the chemical potential energy associated with that mass. And that's a very confusing idea. And the next one is the same way. Exercise helps us lose weight by burning off fat as energy. We often talk about burning off fat as energy. It's in ads. It's in our everyday language. But again, fat is matter, so we should talk about burning it off as CO2, which is what it ends up as.
And in both of these cases, they're gaseous products, and kids very commonly fail to keep track of gaseous products. That they'll do E equals MC squared instead of recognizing that there's a gaseous product.
And in cellular respiration, we say glucose is converted to ATP. That's just being sloppy. What we mean is the energy in glucose is converted to energy in ATP, but none of the atoms in the glucose end up in the ATP, but our language confuses kids. And so that's what makes this all pretty tricky. Do you want to do this one or should I think we can do this.
Yeah, so I think this is, you know, so if kids are going to trace matter and energy, they have to learn to think about what kind of change do we have here, and depending on the kind of change, what's conserved and what's not conserved. So on physical changes, volume is not conserved, like things can expand and contract, and that happens all the time. Whereas mass, substances, molecules, atoms, all of those are conserved. You've got the same atoms, the same molecules, the same amount of mass, the same substances at the end as you do at the beginning. Chemical changes get more complicated. That volume is not conserved. Substances are no longer conserved. You have one kind of substance at the beginning, a different kind at the end. Molecules are not conserved, but the molecules get created and destroyed. Only atoms and mass are conserved. So, you know, the tracing matter and energy is really important, but you can do it only if you're very careful about what's the nature of the change and what's conserved in this change.
So powerful but difficult ideas, I guess, is our message. So we want to pause here and take questions from you. And I guess, Ted, you're going to help us with that.
Yes, I will. Do you want to say anything first, Bryn? I don't know if you're about to hop in or not.
No, that's fine, Ted. We can go ahead and jump into our Q&A.
Okay. So everyone, if you can go ahead and type any questions you have in the chat window, and we will do our best to provide, get Andy and Joyce to answer them here. And I think one piece in here, sort of was being discussed a little bit ago, is do you worry at this level when you're talking with K-12 students about the problems that exist in terms of quantum mechanics and things like that? And the other pieces here is you brought up E equals MC squared as a piece here, and some people will argue about a molecule that is high energy state does have a slightly different mass based on some of these principles.
Right.
What's your thinking about what to do with that?
Well, our thinking is that if they don't understand the simpler model that applies most directly to everyday life, where the mass is pretty much conserved, there's no sense talking about things like E equals MC squared. It is hard enough to learn how to separate matter and energy and keep track of them without the complexities of things like E equals MC squared, or I'm married to an astronomer, things like dark matter and dark energy. We don't worry about those things. We're more focused on a level of understanding that works in the everyday world.
And I think one of the things, we try to think developmentally, and the question is, does anybody ever achieve understanding of relativistic matter and energy or quantumatic matter and energy without going through classical understandings first? And we think the answer is no. It didn't happen historically. We don't think it happens.
Great. Sherry here has a question. At what point in the grade should we begin to think about introducing physical and chemical changes as part of the properties of matter?
The standards bring those up a little younger than what we find is probably appropriate. Certainly at middle school, students can begin to sort out these differences. It's for younger students, distinguishing chemical and physical change is very difficult. We sometimes teach them these signs like bubbles or things like that are signs of one kind of change or another, but there are exceptions to all of those rules that make it hard for younger students.
Think about tracing matter and energy as a cross-cutting concept. I think upper elementary school kids are in a place where they can start to trace matter through physical change. If they understand that when ice melts, you still should have the volume changes, but the mass should stay the same.
Right, I think energy is the hardest side of it.
Yes, and energy at the elementary school level, we'll come back to argue about that in the next section, but our feeling is that kids are in a very poor position to trace energy at the elementary school level. And tracing matter through chemical change at the elementary school level is also something we don't see much evidence of kids doing successfully. We think both of those are reasonable to ask kids to do at the middle school level.
That makes sense. Piece here, sort of off of Carol's question, is do you recommend addressing matter and energy together to try to formally distinguish them, or do you recommend a sequence of really focusing on one for the other, and then, if so, which one? I'm guessing, based on what you just said here, matter would come first if you do them separately.
Right, we think separately, starting with matter and specifically just physical changes. And remember how I started with at the macroscopic scale, the human scale, with an energy example separate from a matter example? I think that's how we would initially start. Students can begin to see the energy changes associated with phase changes. That is, they know you heat things to melt them. But that's about as far as it goes in terms of putting those two together.
I think that very often it makes sense to teach about matter and energy at the same time, but there's definitely a sense that matter is more fundamental. It's the same kind of thing, that we see evidence of kids successfully tracing matter when they're not successfully tracing energy, and very few examples of kids successfully tracing energy when they're not successfully tracing matter.
Which makes sense, because of course it's the matter that we see. The energy is something we talk about, but we can't actually see.
Very good. Well, why don't we go on a little bit here, and we'll take some more questions later.
Okay. So some of these questions are actually anticipating the next section, where we're going to be talking about learning progressions and what we're learning about how students' ideas about matter and energy can develop. There are two things we want to talk about in this section. One is to give a very brief overview of learning progressions and learning progression research, and the other is to give one example of some of the kinds of things that we're talking about in learning progression research and what we're finding about how students' discourse and knowledge and practice change from elementary to middle school to high school. So let's have a definition here. Learning progressions are descriptions of increasingly sophisticated ways of reasoning about a topic. We don't think of them as inevitable, but we think of them as based in part on empirical research about what evidence do we have about how kids actually perform and how kids actually learn at different grade levels. And we've been working with kids from elementary school level through college, and so we've collected a lot of data and we've done a lot of teaching experiments where we're trying to see kids of this age, what are they learning successfully, what are they learning less successfully. As we do this, we're trying to develop three kinds of things, all of which are encompassed by the term learning progression. One is a learning progression framework that defines levels of achievement for a student. A second is assessment tools that reveal students' reasoning. And the third is teaching tools and strategies to help students make transitions from one level to the next. So I want to start with the assessment tools. That I'm about to show you a question and some kids' answers, and I'm going to ask you to take an initial guess about, given learning progression research, and in this case, given your own ideas, which of the answers are the least and the most sophisticated. So here's the question. We call this the eat, breathe question. It says, humans must eat and breathe in order to live and grow. Are eating and breathing related to each other? Yes or no? If you circled yes, explain how eating and breathing are related. If you circled no, then explain how they're not related. Now, we think of this as primarily a matter tracing question. The kids pretty much know, most kids know that you breathe in oxygen and breathe out carbon dioxide. And most kids know that you eat food. And they don't necessarily are not able to connect the eating the food with the carbon and the carbon dioxide. When you breathe out carbon dioxide, you are breathing out carbon that came from the food that you ate. And so a sophisticated answer is going to be one that manages to trace the carbon from the food into the carbon dioxide that's breathed out. And we don't see a whole lot of kids who are doing that. So here are 3 actual responses that we got from kids of different ages. And your task is to figure out what order to put them in. So we've got Kay, who says, yes, they're related because the energy. I'm going to read these, and while I'm reading them, you can feel free to be starting to put your ratings up. So Kay is going to say they're related because the energies made from the cell's respiration can then be used to break down food, such as sugars. You can find other ways to break down food, but without the help of ATP from cellular respiration, the rate would drastically decrease. Then there's L, who says yes. Notice they all say yes, they're related. They're related because eating allows metabolic processes to work inside the body, and breathing allows processes that need oxygen and food to function properly. And then there's M, who says yes. When you eat, the food gets broken down and put into your bloodstream and brought into cells that need energy. The oxygen you breathe in breaks down the high energy bonds in the food. So what's the order here? Which is the least and the next most and the next most sophisticated?
And Andy, we had a question in the chat room though from Tom to clarify. He wanted to know how old are the students who gave these responses?
These were middle and high school students. I think probably all of these were high school.
Great. And so everyone, your poll buttons are open, and you can submit your response based on the options that are showing at the bottom of the screen to show what order you think they should be placed in terms of their sophistication. We'll give everyone a few moments here, and looks like most folks, we've got about...
Remember, the lowest level response goes first.
This one will take a few moments to think through for everybody to get their response in there, so we may give them just a bit longer than we normally do, Andy. But did you want to look at the total of responses on this screen, or do you want to wait until your results slide in a couple slides down?
Why don't we, yeah, let's look at the total responses on this screen, because we don't actually have the choices on
with the other screen.
The other screen, and so we can kind of look at what the majority of, or it's going to be the plurality, the modal answer is here, and compare that to the modal answer.
Great. Okay, so it looks like we've got a little over half with their responses in. Folks, if you can think about putting one choice into our poll button here in the next 15 seconds, we'll give you just a few more moments to pick a response before we move on with our discussion here. And I'll go ahead and lock our poll now so we can take a look at the graph. And I'll turn it back over to you, Andy, to discuss the results. Okay,
so we've got a significant number of people who said none of the above. And beyond that, we've got the most popular answer is D, saying L is the least sophisticated, M is the second most, and K is the most sophisticated.
Andy,
so let's go.
Just one quick correction there. The none category in black there are not responded. E is the.
Okay. So very few. Okay, so very few people said E, and instead of there are a bunch of people who didn't respond. Thanks. Okay, so what we're going to do is we are going to talk about our learning progression research for a little bit, and then come back to these responses and try to say what what do we, how would we rate them and for what reason? Okay, so we're talking about learning progressions, and when you say progression, there's always the question, well, what is it that's progressing? And our take is that we analyze what kids are doing in terms of 3 different things that are progressing. I'm going to start with practices. One of the things that's progressing is kids' ability to engage in the scientific practices such as those defined by the next generation science standards and their precursors. What we see when we're doing the research is kids not engaging in full-fledged practices, but engaging in practices as are possible precursors to those. Then knowledge. We see, again, kids having precursors to cross-cutting concepts or disciplinary core ideas, but the knowledge is partial, incomplete, disjointed, and we need to be thinking about how they put the pieces together to gradually form more complete and coherent knowledge. And then the top one here, discourse, is the one that may be least familiar. But discourse is our word for the ways we have of using language to describe and explain the world. And we find that this is a really powerful idea when it comes to understanding the different ways that kids of different ages explain things, make sense of things. And to illustrate that, so talking about discourse, our notion is that in some ways learning science is like learning a second language, that by the time kids get to school, they're all speaking their native language pretty grammatically. And so that's the first language that everybody gets for free, in a sense. And that language has rules associated with it. This is like the rules of grammar that we were talking about before. So kids master these, and when they master the rules of grammar, they're also mastering in very interesting ways some ideas about how the world works. And those ideas about how the world works sometimes are in conflict with scientific ideas about how the world works. And the tricky thing is that often the ideas are expressed in the same words. So words like energy and matter and weight and material have meanings in everyday discourse, and they have meanings in scientific discourse, and they're not the same meanings. So we can think we're talking successfully with each other when we sometimes are not. So we're going to illustrate that with a single example. We've done a bunch of work with a variety of different examples, but we can't talk about all that now. So here's our example. We live in southern Michigan, and in southern Michigan, there's a common weed called black medic. It's related to clover. The rabbits like it a whole lot. So the rabbits eat the black medic, and sometimes a rabbit is caught and eaten by a coyote. Sometimes the coyote dies and decomposes. So here's a food chain with some matter cycling thrown in. How do different kids understand and explain what's going on in this food chain? When we're working with elementary school kids, we find that for them, this is a story. And you might think of March of the Penguins or The Lion King, something like that. Is that those stories take a form that kids identify with very easily. So the stories work because they've got actors in them, and those actors have needs. And so the rabbit and the coyote need food, they need water, they need air. And we can look at those and say, the kids are saying they need food, water, and air. They're talking about the matter that's cycling into the coyote and the actor. Actually, no, they're not. That they're thinking of those as things that enable the actors to take the actions that are in accord with their purposes. So the animals need food for growth, but that's not the same thing as saying that the food becomes the animals. So elementary school kids do not believe that you are what you eat. They believe that you eat in order to be able to take the action of growing. Now, the plants are there. They're sort of dim-witted actors. They know how to grow, but not how to do very much else. And mostly they're there because the rabbit needs something to eat. And the kids' explanations tend to focus on why it is that plants and animals are doing what they're doing. And tracing matter and energy tends to be pretty far from their ideas about what's important to understand about this food chain. So here's a way we have of thinking about this, that they have a notion that there are cycles going on, and two kinds of cycles are predominant in the kids' language. One of them is what we call the nutrient cycle, in which sunlight enables plants to grow, and the plants feed people and animals, and then the plants and the people and the animals can decay, and when they decay, they send nutrients back to the plants again. And you'll notice that this is both a matter cycle and an energy cycle, but it's really mostly a sequence of events. They're not thinking primarily about matter energy, they're thinking about what causes the next thing to happen. And then completely separate from that, there's the oxygen-carbon dioxide cycle, in which we breathe in oxygen and breathe out carbon dioxide, and plants are very helpful to us because for our sake, they breathe in the carbon dioxide and breathe back out the oxygen. So for the elementary kids, this is really a story about actors. The cycles are sequences of events. Food, water, and air are things that the actors need. And energy is a very familiar word to all of these kids. But for them, energy is the energy of life, or the energy of cause. It makes things happen. It's something that's possessed by living things that gets lost when they die. So that's obviously not what NGSS has in mind as tracing matter and energy. So we get to, so what do kids learn? They can't learn the whole scientific shebang that would correct all of the misconceptions that are inherent in that. They're going to have to learn a different discourse, and they're going to have to learn it gradually. So we think at the elementary school level, we've chosen a very complex living system, and that's not where elementary school kids are primarily going to build their skills for tracing matter and energy. They'll do it much more successfully in simpler physical systems, such as systems that involve changes of state. And some of the things they're working on there, distinguishing matter from non-matter. For a lot of elementary school kids, solids and liquids are definitely matter, but gases are likely to belong over there with the heat and the light and the temperature. They're this ephemeral kind of stuff that doesn't really fit with the matter. So coming to say, no, gases are matter, gases have mass, gases can be converted into solids and liquid. That makes them entirely different from heat and light and motion and temperature. That's a big thing kids are working on at the elementary school level. Another big thing they're working on is how do you decide how much matter you've got? It's not evident to kids at all that weight is a good measure of how much matter there is and volume is not. They're also very unclear about the distinction between density and weight, that they'll say lead is heavy, they'll say this big styrofoam log is heavy, and they have a different meaning for heavy in those two circumstances, but those not necessarily differentiated in their view of the world. And kids can start tracing matter through physical changes. Energy, there are things that kids can learn about energy, but they're not really very relevant to energy as a cross-cutting concept. Mm-hmm. The idea that there is this entity called energy that's conserved in different kinds of situations is something that kids are not really, in our view, going to develop very successfully until they get into middle school and start having a wider array of experiences to work with. So now let's talk about middle and high school. We're going to lump the typical accounts together because unfortunately there's not much difference between the way middle school kids explain matter and energy and the way high school kids explain matter and energy. And in general, what we see empirically today is that middle and high school kids have learned a lot of facts that elementary school kids don't know. And so they can talk about organisms and cells and molecules and things like that. The things that they say are not always correct. They tend to mix up things that are intended to go at different scales, so macroscopic and microscopic and atomic molecular. And they tend to treat matter and energy conservation as facts rather than rules, which is to say, if it's convenient, they'll conserve matter and energy, but if it's inconvenient, then they won't. And the thing about rules is that you follow them all the time, whether it's convenient or not. They also are starting to change some of their ideas about large-scale connections, that they see the cycles as cycles of matter and energy rather than cycles of events. But they still tend to have the separate cycles for oxygen and carbon dioxide and nutrient cycles. So here's a middle school, high school version of matter cycling and energy flow. You'll notice that the energy is still cycling, it's not flowing. And so nutrients recycle both matter and energy to plants. With sunlight coming in too. And you'll see that the oxygen carbon dioxide cycle, most middle and high school students are still got that operating more or less the same way as the elementary school kids do, with the oxygen being converted to carbon dioxide and back again. Well, so that's what kids mostly tell us when we talk to them. Let's try to contrast that with the account of the food chain that we would like to see from somebody who's mastered the next generation science standards. There, we'd like to say the rabbit and the coyote and the medic, they're not actors anymore, they're systems. And those systems are systems that have matter and energy flowing through them, and they're being transformed as they go through the systems. Now, there's this interesting switch that's taken place from elementary school, in that the systems are temporary and the matter and energy endure. And that's quite different from the elementary school kids, for whom the enablers, the food and so forth can come and go, and the energy of life can come and go, and whereas the systems last longer, or the actors last longer, I should say. So they've changed their ideas about what endures and what doesn't. And they also recognize that gases are very much a kind of matter, and that chemical energy is different from chemicals that contain energy. So they know that glucose is a kind of matter, and glucose has chemical energy in it, as opposed to thinking that glucose is energy or something like that. And then the large-scale connections, they now are ready to fully appreciate that matter cycles and energy flows. And so that gets us back to this slide that Joyce showed earlier, saying you've got matter cycling within the system, and notice that it's cycling into and out of the gas phase. It goes from the atmosphere into biomass and then back to the atmosphere again. And the energy is flowing through the system from sunlight to chemical energy to heat and work, and is not recycling. A couple of so let me come back to the responses and our order for the responses. So we thought, and we feel confident on the basis of thousands and thousands of tests and coding responses and looking at the relations with kids of different age levels. The least sophisticated of these responses is L, which is what most people said. That L, you'll notice, is not really trying to trace matter at all, or energy. That L is talking about causes, that eating allows metabolic processes and breathing allows processes that need oxygen. And so that's a sort of what we were talking about as an informal, elementary kind of explanation with some fancy scientific words like metabolic processes and oxygen thrown in there. We find that the second most sophisticated is K, where they're saying they're related to the energy made from cells, respiration, breakdown food. This has got a lot of vocabulary in it, but the more you look at it, the more it doesn't make sense. Like they've got cellular respiration taking place before digestion, and cellular respiration making digestion possible rather than the other way around. And they're not successfully tracing matter and energy. And in contrast, M has really got pretty good. That's not quite completely right, but M is making a pretty clear attempt to trace matter and energy through these different processes. So I think I'll probably have to skip this slide. One of the things that we want to say is that kids' views of what's alike and different change very much, so that for younger kids, systems and processes, living things are all alike, and those are different, whereas older kids organize processes more according to what's the nature of the underlying chemistry. And last thing we'll say about learning progressions is that if you think about the scales again, the general trend you see is kids starting at the macroscopic scale and then gradually being able to connect the macroscopic to smaller and larger scales, and only in the most successful kids getting to the point where they can make systematic connections across scales from the very smallest to the very largest. So this is the progression we'd like to see. What we tend to see instead is kids learning random facts about the smaller and larger scales without being able to systematically connect them. So that leads us to another time to pause for questions and discussion.
Great, thanks very much. So I'm going to start with a question that I had, and with some other folks that had liked the question, is in your discussion of discourse, can you, and you had discourse as a separate category from the practices, can you explain how it is similar to or different from argumentation and the evaluating and communicating information, the last two of the 8 practices?
So I'd say discourse is a more general term. So argumentation, for example, is a practice that involves using words for particular purposes. And people in informal discourse have different kinds of arguments from people who are using scientific discourse. So the claims, evidence, reasoning framework, for example, is very much a way of classifying what people are doing in scientific argumentation. But if you look at everyday arguments of kids on the street, they aren't all necessarily following a claims, evidence, reasoning framework at all.
So discourse is the broader term.
Yeah.
Okay, so there is some level of overlap, but a broader piece here. That's helpful. So looking for some other questions here. Andrea asks, if energy flows, it must go from one system to another, given it is also conserved. Can you give an example? So I think someone is checking their pieces here.
So in the example we were talking about, there's energy flowing from the sun, and it's going into the medic, and then some of that is leaving. Some of the energy is leaving the medic as heat through its own metabolic processes, and some of the energy is passing on to the rabbit. And similarly, the rabbit is losing energy as heat, and at the same time as the rabbit is passing on energy to the coyote. When the coyote decomposes, then that energy goes to decomposers, and it ultimately all gets lost as heat. So there's none of the energy of the coyote and the decomposers that actually ever gets back to the plants.
So it's still in that system, but it is no longer in a useful form. It's all still there. It's conserved, but the form has changed.
That brings me to a question that I've had sometimes when trying to sort of set up systems and work with students. The issue of, do you consider the environment itself to be a system, or do you give it a different classification as such as the environment? And have you found any, in your work with students, does that work well to talk about label the environment specifically in that way? Or I'm just curious how you address that in sort of tracking different energy and matter.
Well, one of the big problems that students have in conserving matter and energy and tracing matter and energy is drawing the boundaries of the system. And so, if you say, I'm going to look at a growing tree, within the tree itself, matter and energy are not conserved. You have to say, I've got to look at the tree, plus the atmosphere, plus the soil, plus the water, and then we can start tracing matter through the system. I don't know that, there are usually aspects of the environment that need to be included in the system that you're talking about.
I think environment is one of those words that we all use in different ways, and we simply need to stop and define when we use it with students. And system usually is a better word. It causes us to think about boundaries, and I think that's what we need.
That makes sense to me. I've always struggled with the aspect of when you talk about the system, the environment of the system, is that the boundaries, the other edge of the boundaries is kind of ill-defined, and
right. Yeah.
Get confused. All right, why don't we go on to some of your next pieces here?
Okay, and we just have a very brief set of things to talk about with respect to teaching students to trace matter and energy. We could talk about this all day, of course, and we're currently excited about work we're doing with the Great Lakes Bioenergy Research Center and about work we're doing with National Geographic to have a matter-energy oriented curriculum that'll be available on the National Geographic website in a couple of years. And some of the examples come from that work. But three things we want to talk about: conservation laws as rules to follow, inquiry into tracing matter and energy, and modeling matter and energy and connecting scales in the process. So we are convinced that kids are going to trace matter and energy only if you tell them that they have to. So we're thinking about saying, here are some facts about atoms that you always have to keep in mind. They last forever in physical and chemical changes. They make up the mass of all materials. They're bonded to other atoms and molecules. Two facts about energy: also last forever in physical and chemical changes, can be transformed from one form to another. And whenever you're talking about anything, unless it's a nuclear change, which is very rarely the case in the K-12 curriculum, then you've got to follow these rules. And anytime you fail to do so, well, that's got to be something wrong with what you're saying. So every time you say CO2 is converted to oxygen by plants, it's like, whoa, wait a minute, are you following the rules? What about those carbon atoms? They don't seem to be lasting forever. So we have to say your explanations and predictions must use what you know about matter and energy. And if you do that, we can use those facts to interpret what happens during inquiry activities. So here are some examples of kinds of inquiry that we're doing. Tracing mass has become a lot easier in recent years because you can now get hundredth of a gram scales for less than $10. And so you can do very precise mass tracing experiments. And you also have indicators such as BTB, which you can use to identify chemical changes. So with tools like this, you can engage kids in inquiry where you're asking them to trace matter and energy. And this involves using those rules. So if you see a change in mass, then you know you must have had some atoms moving into or out of the system that you are weighing. If you see changes in chemical indicators through such as BTB, then you know you must have had some kind of chemical change. The atoms must have somehow rearranged into new molecules. And if you see changes indicating energy, such as temperature change and light and motion, then there must have been some kind of energy transformation. And if you're observing these forms of energy at the end, they must have been there at the beginning. And finally, connecting scales. When we think about modeling matter and energy, we've spent a bunch of time saying, how can you involve kids in keeping track of how atoms and matter and energy are all conserved in chemical changes. So here's a complicated one. Here's photosynthesis. And we have activities where kids, they make a bunch of carbon dioxide molecules and they make a bunch of water molecules, and they've got a bunch of light. The twisty ties represent light coming in. So these things are going to have to be conserved. So you end up with oxygen molecules you end up with a glucose molecule, and we're teaching them that carbon-carbon and carbon-hydrogen bonds, reduced carbon, is a sign of a high-energy bond. So this light energy that came in is now all tied up to these high-energy bonds in the glucose. So what we're trying to do here is help kids trace matter and energy through the process of photosynthesis using molecular modeling to show how what's really happening is you're rearranging atoms into new molecules, and showing how balancing chemical equations, which is this strange, mysterious thing to do, is really nothing but a way of keeping track of those atoms as you're rearranging them into new molecules. And similarly with tracing energy, by using the twisty ties, we can have units of energy that kids keep track of. And we're particularly interested in kids noticing when the chemical energy is the most difficult concept, and say, let's notice that when you've got these reduced carbon and hydrogen bonds, that's a sign that chemical energy is available by combining this particular substance with oxygen. So there's a ton more to say about instruction, but we are out of time, and so we will do our last pause. Let me give us credit for photos that we grabbed from the internet. Thanks to funders, especially the National Science Foundation and the Great Lakes Bioenergy Research Center. And then the final pause for questions and discussion.
Thanks, Andy. What we're going to do is I'll go through a few slides here about some resources we have here at STA. We'll let the teachers, our participants, fill out their evaluation, and we'll then take some questions after that point.
Okay.
So I just want to point out that discussion is that first off, to find some information about the standards, you can go to the Next Generation Standards site here, nextgenscience.org. You can also find the standards and a lot of other information at NSTA's webpage around the standards, nsta.org/NGSS. I want to point out that we have a discussion forum about NGSS in the Learning Center. We also do have a listserv for NSTA members only that's specifically devoted to NGSS. I want to point out some short courses we have going on. I hope some of you had a chance to participate in a series we have going on about formative assessment by Paige Feely. We have coming up here also a session in May about visualizing K-8 engineering education with Christine Cunningham and Martha Davis from the Boston Museum of Science. They are involved with the Engineering is Elementary programming, so you can sign up for that. 3 live session dates. Registration is still open. We have coming up some additional web seminars. I want to give a quick note to everyone that we've had some presenters who've had some scheduling difficulties. We may change the order of these web seminars in terms of what is dealt with on each date, but we will get you that information as soon as we have it confirmed. But just as a heads up about that we may be moving these 3 around in terms of which is done on which date. And I appreciate your patience and being aware, keeping an eye out for that information. I hope that some of you will be able to attend the STEM Forum and Expo in St. Louis, Missouri, May 15th through 18th. I'll be out there talking about NGSS. We have a number of different sessions that are focused on NGSS. And finally, I want to point out here that, as I've mentioned before, you can get a number of publications from the NSTA bookstore. We've got available right now the framework and NSTA's Reader's Guide to the Framework. We have the Reader's Guide to the Next Generation Science Standards that I think you can get right now, an ebook, and it'll be another week or 2, I think, before the hard copy will come out. And this summer, the National Academy is printing, make it a print version of the standards, and you can start and pre-order that at the NSTA bookstore as well. We've got, looking ahead in the fall, we have our various area conferences, all of which will have a number of things about NGSS, as will our conference in Boston next April. And with that, I want to thank Andy and Joyce for sharing their work and their understanding of energy as a cross-cutting concept. Give a little hand of applause to everyone, and pass things off to Bryn to get folks to their evaluation.
Thanks a lot, Ted, and again, a big thank you, as you said, to our presenters, Andy Anderson and Joyce Parker from Michigan State University. And I wanted to thank you as well, Ted, for your facilitation of our Q&A tonight, helping out with our discussion. Thank you so much to all three of our presenters today. And a big thank you to our participants as well. Thank you for sharing your comments and your questions. It was great to have that in our discussion today. We would like to thank the sponsor of today's web seminar, the Carnegie Corporation of New York. And a thank you to the administration of NSTA for their support for web seminars. I'd also like to point out the upcoming programs on our web seminar calendar. You can come join us tomorrow for NASA Explorer School's Chemical Elements, Genesis, What Are We Made Of? On Thursday, May 2nd, another in our NASA series, Temperature and Earth Climate, Modeling Hot and Cold Planets. And then come back with us next week for a great STEM program from NASA, Pythagorean Theorem, Exploring Space Through Math, Lunar Rover. You can register for these programs and more upcoming web seminars by going to learningcenter.nsta.org/webseminars. Thank you again, everyone, for your participation, and we look forward to seeing you again soon on another web seminar.